the other red paper, and it's on multiscale change pointing.
Thank you, Paul. Thanks for the organizer to invite me to talk here. I should mention my background is not at all in time series, so I learned a lot already, or I think I learned a lot. So this is joint work with essentially 3 people. I would like to acknowledge Klaus Frick, who is a former postdoc of mine now. He's in Switzerland. And Thomas Hotz, who is in particular involved in the development of the R package, step R. I will comment on it at the end of the talk. And Hannes Seeling, who is a PhD student, and he is going to defend, I think, next week his thesis. So whatever difficult question you raise here, I will be very happy to get it, and then I will forward it to the defense of Hannes. So I'm really looking forward to that. Okay. What I would like to address a little bit is the issue if you have a piecewise constant function with you might call it change points. Here you have 3 of these change points, or I call it jumps, and you have linear segments between. Then you want to do, based on your data, which are the blue dots, somehow a kind of decomposition of this data into these pieces of segments. And of course, there has been done a lot of work, and we got a very nice overview talk by David Sigmund, who addressed many of these things, so I need not to repeat that. But in particular, recently, and also David addressed that, is that besides of statistical efficiency, in order maybe to estimate the locations of these change points or the sizes or whatever, also a computational issue came into the game. In particular, if you think about high throughput data, or if you think about, for example, comparative genomic hybridization data, which David was talking about. So we are faced with several millions typically of data. So the question is there a way to do efficient inference? And I really emphasize here inference. That means not only the reconstruction of the signal, you would maybe like to come up with a confidence band or with certain probability statements, for example, about the number of these change points or the number of these segments, and to do it still in a computationally most efficient way. So that's what drives me in this work. I should mention, David already mentioned a lot of very important names. I also should mention maybe John Tukey, and also David Blackwell and Arrow and others. And Tukey, I think, coins the name of a regressogram. And he said, well, if you have normal data and you would know these locations of the change points, then it's easy. You just take the local averages and then you are done. So from a maybe modern perspective, that's not quite true anymore. But essentially, what he pointed out is that the difficult issue is somehow to estimate these locations of the change points. So we will do that. What I do, in a sense, is I try to combine 2 different things, an estimation and a testing step. And David already gave a very nice talk on multiscale testing issues, and I will just repeat it in a sense in a maybe very naive and graphical way. Assume the following. Here you get a bunch of data. These are these gray dots, right? Later on I show you the signal where they came from. And let's assume you have a candidate function. Let's, for example, this red one. And you think this might be a good reconstruction of your piecewise constant function. So what could you do in order to check that? You could do a residual analysis. So here you see a plot of the residuals, right? That's what I have done here. So for example, just visually, you already see that in this pattern, if you believe that these data are IID normal around that function, you see here, for example, locally a certain pattern where you might think that there could be a deviation and you should include a jump here. So how can you formalize that? The first thing what you could do is you could look at the overall distribution of the residuals, and you could see whether they are normal. So, but here a global inspection of this residual is not really a sensible way to do, as you, for example, see here locally. So you want to localize that. So what you could do is, for example, you could take a fixed window, let's say maybe of size 10, and this is what I call a scale, so that would be a small scale. And then you could locally test on this residual pattern by performing a t-test, whether your signal is 0, whether you already have filtered out that signal properly, right? So you can do that, for example, at that window here. You can do that at all windows, and this is why it's sometimes called a scanning method or a scanning statistic. So if you do that, then, for example, for this residual pattern on this small scale, you find violators. That's what I have depicted here. So it seems that on this small scale, something goes wrong here. So that's a deviation from the assumption that the residuals are just IID normal with standard variance. Let's assume we know that in this case. So you do that on larger scales, like, for example, this one, right? This is roughly 100 data. And you, again, scan through the whole residual field, and then you get a certain set of violators. So you can do that essentially on all scales, and you perform this local t-test properly standardized on all these scales, and then you get a set of violators, which I have depicted here. So a blue region always means that there is a violation on a certain scale. So, for example, this is scales with lengths 16, 32, 64, and so on. This is just the dyadics. You can do it on all scales, but just to visualize it simpler. And then you see, for example, on this large scale, there seems to be something going wrong, which means on this window of that size, there seems to be a violation of this signal 0 assumption, but also on small scales like here or intermediate scales like here. So now what you can do is, in fact, this candidate function was the maximum likelihood estimator under the assumption that you believe that there are 4 jumps. The global maximum likelihood estimator under that assumption. You don't know where the jumps are, you don't know how large the sizes are, so you can compute that. So you include one jump more. This would be the maximum likelihood estimator under the Gaussian assumption, including 5 jumps, and then you see that in this residual pattern, it seems that here you start to do things much better. But still there are some violators on certain scales. So you include one jump more. Now you are at 6 jumps, which means 7 segments, 7 jumps, 8 jumps, and so on. And then the first time you don't see any violation on any scale anymore is here the solution with 8 jumps. That's the global maximum likelihood estimator, which I just have chosen as a candidate function. And now this local testing idea would tell you that there is no violation on any of these scales anymore. Of course, there is now lots of issues. One issue is multiplicity, right? We performed a lot of tests on the same data set, and the question is, somehow, do we control the overall error? We will see that this is in fact possible, and also David, of course, I explained it very nicely a lot about that. But moreover, what we want to do is, we do not only want to check, in a sense, or to test whether a candidate function is appropriate. We would like to come up with an estimator, which in a sense is tailor-suited to that testing idea. And what we will see is that we get from that testing idea, in a sense, for free, also a uniform confidence set for that function. Whatever the number of jumps is, we can do it for an arbitrary number of jumps. We will get some theory and see that. Okay, so we want to combine these two rules. So let me now do that testing, and this is just repeating essentially what David said. Do that testing a little bit more precise. And to that end, I would like to work in a very simple model, and there are now many generalizations of that and extensions. But the model is, for simplicity, let's believe that this is just a Gaussian regression model. And for simplicity, let's embed our change point function in the unit interval. That's what I did here. And we have an equidistant sampling. And we have a certain number of change points. I call this number k. That's an unknown number. It can be arbitrarily large. You have no bound, but it's a discrete number. And I'm working for all the theory in the space of, to make it mathematically correct, in the space of all right continuous locally constant functions with an arbitrary but finite number of jumps. Okay, so that's my setting, and I believe that my signal is in that space. And for simplicity, I assume that the variance is known, else you can estimate it from the overall data. Okay. The set of discontinuities or jumps of a specific signal or function theta I call j of theta. So the number of jumps is just the cardinality of that set, because all these functions have a finite number of jumps. Okay. Okay, so what can you do? Exactly what we did visually before. You can take a window of length j minus I plus 1, right, from I to j. And then you can test for local constancy. And it's more convenient to test for a fixed constant value theta 0. So what could you do if you want to do it statistically efficient? You would employ a likelihood ratio statistic, right? So that's what I have written here. And you can generalize, as I said, we did it in our paper to exponential families, but you can go far beyond. But I will stick here just with the Gaussian case to keep things as simple and clean as possible. So in the Gaussian case, the likelihood ratio statistic would just amount to that t statistic or the square of that t statistic. So you do that for a fixed window. And now the idea is the following, and this is now a little tricky. We do essentially the same as David presented yesterday. So we look at the maximum over all these local statistics. The square root comes just from a standardization that asymptotically things stabilize. But what we will not do is we will not do it on all, and there is a reason, a computational reason for it. We will essentially not do it on all the intervals. What we will do is, in a sense, think of it that you have a candidate function, exactly as I presented you before, and then I take the pieces of constancy of that candidate function and I perform such a multiscale test, the maximum addresses to the multiscale, on all these constant segments, and see on these constant segments whether there is a deviation from constancy. That's what I do. And then there is another term which is important, and that's what I call a scale calibration. And the scale calibration, in a sense, I will show you in a second the picture, in a sense, does the following. It puts the power of all these multi-scales tests on equal footings, because of course this depends on the length of the scales. If you have a lot of data, that's somehow different than if you have just a few data. And it turns out that such a logarithmic term here, which you subtract, so that means you somehow penalize the longer the scales are, you somehow penalize it more. This is, in a sense, an appropriate way to do that. There are other ways. For example, if you have prior information and you think or you believe that the action is only going on very small scales, you could leave out that term or you can modify it. But what we'll see, we have theory actually which gives you a kind of overall very good statistical performance in order to introduce such a term. So essentially, I think this term the first time popped up in a paper by Lutz Dümken and Volodya Spokojny in 2001. And to motivate you, I will not give you a theory here, but to motivate you, the idea of this term is, imagine you would look at that scale statistic which doesn't have this scale calibration. Then actually, if you look to the distribution of the maximum, you can compute it in that case. It converges to a Gumbel extreme value distribution. But what it also says is actually that essentially the maximum is always attained on scales of a logarithmic length. And that, in a sense, means it's not really a multi-scale thing. You only look for the small scales. And there is theory which actually explains that. And what you see here is just a simulation. If you take that limiting distribution and you look whether it exceeds a certain quantile or threshold, you see that essentially it's always exceeded on these small scales. So if you include that scale calibration term, you see that roughly the distribution becomes uniform. So it's really distributed over all scales. And that's what I mean that you put the scales on equal footing. OK, this was about the testing part. And now we come to the estimation part. And the idea is the following. And it has forerunners. I should mention a PhD thesis by Hohenrieder and a paper by Davis and also our own work. And the idea is now, think of that multi-scale statistic for simplicity as a ball. It's not a ball, but it's a convex set. And what you get now is you get control with that convex set that on all scales, the fluctuation of your signal is controlled in a uniform sense. That's what it says. So let's write this as a constraint. And let's assume this multi-scale ball or multi-scale set is less than a certain constant. We will talk about the choice of this constant later on. And then what you do is, within that ball, you try to find the simplest function, in a sense, depending on your model. Now your model it's a locally constant function. Try the simplest function. That means the function with the fewest number of jumps. And and you minimize within that multi-resolution set. This is a non-convex minimization. It's really an L0 minimization, right? So you minimize a number of jumps. That's a non-convex set, but remarkably, you can, because typically this would lead to an NP-hard problem, but remarkably here you can actually come up with algorithms which are, in the worst case, just quadratic in the number of observations. I will come back to that later on. So assume we can compute that, right? Then we get a solution which in first order the number of jumps of that solution will estimate the number of change points of our problem. That's the first thing what we will do. So in a sense, we solve the model selection part of the problem in the first order. That's what we do here. Now, if you have solved this model selection part, given your data, you can compute that. You get a certain number, let's say 20, right? And then what you can do is, you can look, and you also can compute that very fast. You can look at the set of all theta, that means of all possible jump functions, with that number of jumps you have estimated from the data, which fits into that multi-resolution norm. Actually, it's not a norm. It's a convex set. Okay, so you get a set, and let's assume we can compute that set. And what I claim, and we'll show it later on, that this set has very good covering or confidence properties for the entire problem. So now it comes to the estimator. And here we really violate actually the regressogram idea. We just don't take local averages. What we do is we follow a local likelihood idea, but what we do is we squeeze actually, in a sense, our estimator to fall in that set. This has certain nice properties. So you compute the maximum likelihood estimator, you know now the number of jumps, but you do it constrained in that multi-resolution set. That's our estimator. And let's assume we can compute all these things. Okay? That's what we do. So the only, in a sense, unknown number here is a Q, right? And obviously the Q, in a sense, drives the parsimony of your estimator. If you relax the Q, that means if you make it very, very large, then there is almost no constraint. Then what would happen? You would just minimize that functional without any constraint, so you get just a constant function. If you make this number very, very small, then the set of solutions, right, is of that type that you only allow very small fluctuation from your data, so you will include a lot of jump. So it's like a regularization parameter or a smoothing parameter. But I will show that in a minute. It has, I think, a quite nice statistical interpretation. Namely as a confidence parameter. Okay, so in order to calibrate that Q, or in order to select that Q, what we advocate, but there are other ways to do that, is, for example, and this really depends on the problem, think of that you would like to minimize the probability that you misspecify the true number of jumps. So imagine you are in a situation where you in first order are interested in the number of jumps. Maybe not so much in the size, but in the number. There are other ways to do that, but let's stick with that. And you want to do that, and you should keep that in mind always uniformly over that huge model of locally constant functions. Okay? So that's what you want to do, and I call it the model selection error. And you would like to find that Q in order to minimize that guy. That's the idea. So if you look at this error, it consists of two parts. There is, in a sense, an easy part and a difficult part. The difficult part is a red one. And that's that you want to control the probability that you underestimate the true number of jumps. I come back to that. And then there is an easy part, in a sense, and that's the probability that you overestimate the number of jumps. I call it the undersmoothing error, because if you overestimate the number of jumps, right, then you include more jumps than actually necessary, so you get a not very smooth solution. Okay? So let's start with bounding this error. So here is a very simple argument, and this argument is very general, and it works essentially for all types of statistics where you minimize a functional under such a constraint. And there is many of these statistics in different areas of statistics, image analysis, and so on, which all follow the same idea in a sense, or the same principle. I called it multiscale Danzig generalized Danzig selectors, but that's a different story, which links it to high-dimensional statistics, essentially. So imagine what we want to do is we want to control the probability that you overestimate the true number of jumps. Now think, if your estimate, right, has included more jumps than the truth, whatever the truth was, then this necessarily means that you violate your constraint for the true signal, whatever the true signal was. It had more jumps than it had less jumps that you included in your estimate. So you get this simple bound here. And now it somehow remains to compute the asymptotic distribution of that multi-resolution statistic. Or maybe come up with a finite sample bound, and then you can bound that error. So what you can do is actually, I will not write it down in detail here, it's a little messy, but asymptotically you can compute the distribution of that statistic as n goes to infinity, and it converges essentially to a sum of maxima over such a functional of a Brownian motion. E is a Brownian motion. And that this variable exists is actually not completely trivial, and it has been shown by Dümken and Spokojny. In our situation, we get, and that's maybe a nice link to what David talked yesterday about, we get actually in the asymptotics explicitly the logarithms of the differences of successive jump locations. What is interesting, what you should keep in mind is for bounding this overestimation error, the size of the function does not play any role. It's really only the locations of the jump. So you get control over that. You can simulate that, for example, as an upper bound, as a simple upper bound, or you can do more refined things. For example, if you have some prior knowledge about the distribution of these locations of the difference, you can simulate or you can compute the asymptotics or simulate the finite sample statistics. And then you can choose your Q in such a way that you get really control over that overestimation error. Okay, so here is just the simulations of this statistic here for different sample sizes. So you see, it's a nice limit distribution. Okay, that's where we are so far, right? We can control this error. So you fix an alpha level, let's say 10% or whatever, and then you can simulate a Q or compute it theoretically, such that you can make the following statement with, let's say, probability at most 10%, I overestimate the true number of jumps, whatever it was. Okay? Okay, so far the strategy. There is a very nice saying, however beautiful the strategy, you should occasionally look at the results. And here in UK, I think everybody knows who said that. It was Winston Churchill. There is a German way of saying it. Gray's old theory, crucial is on the football ground. A great philosopher. It was Alfred Preisler, former Borussia Dortmund captain. So it's essentially the same. So let's see how this works. What you see here is the following situation. It's the same data essentially as before. The black function is the truth, that's the signal. The red function is the estimator. The gray area is the confidence set or confidence band we get out of that construction I gave you before. And here, the error is very small, it's 2%. Right? So that means you want to control the probability that you overestimate the true number should less than 2%. So what you see, what happens is that you miss this jump location here, right? Because you really have to give a very strong guarantee. But now let's run the alpha, and then you see the dynamics of this estimator. That's what I'm doing now. And then you see that at about 20% here, it has started to include that jump. And then the solution just remains persistent for a very large range of alpha levels. And then at some point, if alpha becomes very large, I think larger than 0.9, then you start to relax, of course, this probability very much, and then you start to include, now it should happen, additional jumps here which are not present. Right. So for example, if you pick out any solution between 0.2 and 0. Oops, sorry, my mistake. I want to go here. If you pick out any solution between roughly 0.2 and 0.9 here, you get essentially always the same reconstruction. Here you get the estimate for the location of the jump. You do it a little wrong, but you estimate the number of the jumps in all these situations correctly. So what are these blue arrows here? The blue arrows are the confidence bands or the confidence intervals you get for the locations of the jumps. And the gray area is a confidence set for the entire function. And what we claim is we can get control on both. Before I do that, we have to talk about the other error, the underestimation error. So what you would like to do is now you would like to bound the probability that you underestimate the true number of jumps. If you think a little bit, then you immediately realize, of course, that this is not possible per se, without any prior information. Why? You have a finite sample of data, and now imagine the situation that you have a function which just between two data points makes a little jump, or another little jump. You never can see that. So you need prior information, at least on the smallest scale for these jumps, in order to get any control over that error. Asymptotically, all these effects vanish, but you can see that with that little situation, and you can do theory for it. So here is an exponential bound, which is quite tricky to prove, for that method for the underestimation error. And what enters in that bound, and you can play a little bit with it, it's just in the normal case. You can generalize on that. It's the true number of jumps, whatever it was, and we have expressed it here, and you can do that not only for the smallest scales, you can do it for essentially all scales, but here is the simplest version for the smallest one. Imagine that you have a signal where on the smallest scale the jump size is capital delta. And the smallest scales means that's the smallest interval length, which I call lambda, where a jump happens, right? So to any signal, you can, with a finite number of jumps, you can look at the smallest interval where a jump happens, and you can look at the smallest size. And then you can express this underestimation error in terms of these quantities. And so what you see essentially in this exponential inequality, there enter two terms. The first one is the Q. The Q was the threshold for the multi-resolution ball. And the second what enters is, in a sense, the standardized signal-to-noise ratio. And it enters exactly in that way what optimality theory would predict. So you get the smallest signal, the smallest interval length times the delta divided by the standard deviation of your noise times square root of n. So that means what you can do now is you can use that and plug in prior information of these quantities and then use it to control the error that you misspecify the number of jumps. And that's what we're now going to do. Okay, so we have control, to sum up, we have control to overestimation of the number of jumps. We have control to underestimation, but the underestimation control is such an exponential bound which depends on the smallest scale and the smallest jump size on that scale. And more refined inequalities are possible, but I will not go into detail here. It becomes very technical. So what we can do now is we can construct confidence sets where we really can say something, at least to some extent, about its covering property. And we will see that from that bound we get uniform convergence of the jump locations and the jump sizes and the function itself. And we all express everything in terms of the smallest scales and the smallest signal strengths. So here is just to sketch one application. The probability that the true signal is covered by that confidence set, which now depends on that threshold Q, right, is the probability that, first of all, you fall into that multi-resolution region, and second, that the true number of jumps is not smaller, the estimated number of jumps is not smaller than the k. So you can decompose it in exactly these two areas we've seen before, and then you can prove the following. You can, for example, prove if I have a sequence of models, that means functions, jump functions, in such a way that the smallest scale where a jump happens times the square of the smallest jump size is roughly of the magnitude of log n over n, then you can show that the confidence level is kept uniformly asymptotically as n goes to infinity over the sequence of spaces. So it's a sequence of spaces, and each space is delimited by that scale condition here. And we claim that you can actually not go beyond. I tell you later on a little bit. So this would be the theoretical property of the confidence set, at least. Now you can play with that ideas a little bit. For example, I will be very brief here. You could say, well, this method, first of all, is really designed that you want to control the error to overestimate a number of jumps. You do not want to include too many. But there are situations, and David talked about it, for example, in genetic screening, where actually this is by far too conservative. And in these situations, maybe you want to relax that error. So you can, of course, do now the same thing. You can, for example, take a convex combination of these two errors and cook up the same recipe. Or you can incorporate Bayesian ideas, like you have certain prior information on that smallest scale and the smallest size, and then you can try to maximize, that means try to determine that level Q, that you maximize the posterior expectation of such an expression here. What we do is, and that's also implemented in our software, essentially we take a default setting of that size, because this is essentially the smallest detection rate you can get. And from that you can compute the lambda and the delta. You get two equalities here. And this says, for example, that you put, in a sense, the size of a signal and the length of the scale on the same footing, because the difficulty to detect a jump is of the location of a jump is of order 1 over n, and the difficulty to detect the size is of order 1 over square root of n. So you can say, well, I put it on the same footing, but that's an arbitrary choice. You can also put some prior information in it, and then you get different rules. But it's all about how to choose essentially that Q. There are other strategies, for example, by Chen, Chan, Summers, who came up with, they call it smooth sub 2, came up with a method which calibrates better the confidence coverage of the confidence set, but I will not go into detail here. There is room for improvements. So how does it work? Here is an example. So this is the data we've seen before, right? Now let's assume we have prior information. So here's the prior information would be that I believe that on the smallest scale, the signal, the smallest scale is here, the signal is larger than 0.2. Let's say we believe that. Or other things we are not interested in. And let's also believe that we have a bound for the number of jumps, let's say 10. Then what I can do is I can compute a posteriori, given the data, the probability, which is that red line, that I underestimate the number of jumps. This probability was depending on this data, and I have an exponential bound for that, so I can do that. Given this data, that's this line here. And what I also can do is, of course, for this I don't need the prior information. I can compute the probability that I overestimate the number of jumps, right? Because I have this finite sample or asymptotic distribution of that multi-resolution statistic. So if you sum up these lines, right, you get the probability that you do not estimate the jumps correctly. The probability of overestimation plus the probability of underestimation. That means the probability of not estimating the number of jumps correctly. So you get this function here. So given the data, what you can do now is you can choose, for example, the Q in such a way that you take the minimum of that function. And this would give you a probability, which you can guarantee, but in a sense, the best possible way to control that error. For this prior assumption, it's roughly 0.5. So that means I would claim that given this data, this is my reconstruction, I would know with a probability of 50% that I got the right number of jumps, whatever it was, in a kind of uniform sense. Okay. Of course, if you come up with stronger prior information, you get better things. So here is just one application. I'm currently working on several, I'm interested in several applications, in particular in genetics, but here is one which essentially brought me to the whole area. And this is from biophysics, very briefly. this is about what is called ion channel recordings. And ion channels, as you maybe know, are sitting in the outer cell membrane, and they essentially regulate the whole channeling process of cations, of water, and so on in the cell. And there are so-called single molecule experiments which essentially date back to Erwin Neher and Bert Sackmann, who got the Nobel Award in the mid-90s for that. And this is a very sophisticated technique, which is called patch clamp technique, and there are many variations on it. And the patch clamp technique, in a sense, allows you to put such an ion channel. Actually, these are artificial ion channels, which are synthesized in the lab of Claudia Steinem, a colleague in chemistry in Göttingen. And this allows you to measure for a single channel the so-called gating properties. So without going into detail, what you see here is essentially, you see here the voltage, for example, of such a response. And there is a lot of noise. That's what you see here. And then that's what we claim here. And then there is this gating, and you see that, for example, here it seems that the channel is closed. Here it is open. That means ions can go through. So you observe a higher current. Here it's open, and maybe here it's closed, or here it's in intermediate state. That's not clear. So this would be the data, for example, and that this is what we would get, for example, with our method. So this is a gramicid 8 channel, which is just a kind of test system which has been studied for a long time. In order to do some sensible data analysis, I have to mention at least the following. Things are a little bit more complicated. If you look at the raw data, there is a huge fluctuation. And what you do is you apply essentially a bandpass filter in order to get these very high frequencies out. Here, in this case, the bandpass filter is known, or you can estimate it from the data. Essentially, it amounts to the following. It amounts to a convolution of the signal with that filter. So actually, you do not really believe that it's a completely locally constant function, but this is on very, very small scales, actually, like 50 data points. This was a sample of a few 100,000. So you get a function which actually is locally smooth and not really a jump function. But on that scale, it doesn't matter. And then, because this also applies to the observational, to the error, you get a correlation. It's just stationary correlation, very simple. So what we do here, for example, is we just take our local likelihood ratio statistic, divide it by the variance which now comes from that model in order to calibrate it correctly. So you have to take into account the autocorrelations, right? We ignore the very small scales. That means we just look at those fluctuations beyond this bandpass filter, and then we get the following. And this is current research which just has been accepted together with a lab in Göttingen. And what they do is they modify actually these channels, and that's a so-called acylated gramicid 8 channel. And what is now important or interesting is that there are theories that so-called subgating happens in these channels, which means actually that you do not have really severe opening and closing states. You have somehow intermediate states. And there are theories how these intermediate states can happen. So I'm not a biochemist, so I cannot tell you about the details. I know a little bit about it. So here is the signal. That's what you see. And this is what our method gives. And what is here important is we really want to show that subgating happens. So that means we really want to control the probability that we do not overestimate the number of jumps. Because if we start to overestimate it, then of course we start to include a lot of fluctuation in the signal, but I do not have any evidence for subgating. So we made it in a very conservative way, right? So that's what you get. So if you magnify, for example, this part, then you really see that there on the small scale behavior, there seems to be really something like subgating. That's an intermediate state. And you find this actually here in that area, and you also find it here. So what we claim here is that we really have statistical evidence for 2 subgating states. So if you take the overall data, for example, and you just make a histogram with a usual histogram width, and my colleagues from chemistry insist on plotting histograms, I should mention that. So I'm not so fond of doing histograms, but they insist on doing that. So if you do that now for this blue function, then actually you see really 2 severe modes here, and also another mode here, which somehow really shows that you have two subgrading states. And that's also what our theory says. Okay, how much time do I have? 5 minutes? Thanks. Very quickly, a few remarks. We got very interesting comments, and I'm very grateful to the discussants of our paper so far. Very interesting and thought-provoking comments. And we are currently working on it, and I try to address some of them. Before I do that, let me just mention very briefly computational issues. In fact, what is very important here is that you can, and that's quite tricky, that you can actually compute the smooth, this estimator, and together with its confidence sets, in a maximum of n square steps. In fact, it depends on the final solution. So you are usually somewhere between linear and quadratic. It really depends on how many jumps you include. The more jumps you include, the faster you are. And this is due to the recursive structure of the dynamic program. We also used to fasten up our algorithms nice ideas, what they call pruning steps in the paper of Rebecca Killick and co-authors, which we found very useful here. But I will not go into detail here. Another issue is, and I attached it very briefly, and we have theory for it, we can actually show that this estimator has the following property. It has a property that if the signal has a single change point, a single jump, wherever it is, then there is what is called the optimal detection rate. That means you look in the set of all tests, what would be the optimal test in order to detect this change point, and then you can actually relate the scale and the size of the jump and the number of observations and the variance in order to compute that optimal detection rate. That means you want to have a test which does not reject falsely with let's say 5%, but the power, that means to find the jump, should be at least larger than 5%, or larger than alpha. And then you can compute this detection boundary, and there is a rate which I do not display. And then you can show, actually, that's very simple. Oh, it's not so simple, but it's based on arguments of Yuri Ingster and others. You can show that square root of 2 is the constant in this optimal detection rate. And we can show, actually, that we achieve that constant. And this constant is known to be optimal for a single change point. For a bounded number of change points, we just get a constant which is slightly worse, which is 4. We believe that's the optimal constant, but we do not have a full proof of it. And for an unbounded number of jumps, we get just get the number 12 here. So you see really that, in a sense, we would claim that at least asymptotically, the detection properties of this method, which is essentially due to the efficient likelihood ratio statistic and due to the scale calibrations, are pretty good. There is a paper by Tony Kai and co-authors who explicitly assume sparsity in their signal. And then they can cook up an estimator which is based on that sparsity assumption, which also get that assumption. What I would like to stress here is that this change point problem really allows to do inference on all scales simultaneously without any sparsity assumption. So it's really different from high-dimensional statistics, and it's also different from parametric low-dimensional statistics. It really sits between. So that means the dimension of the problem, if you want to say so, is really n, and not much larger than n, but also not much smaller than n, the number of samples. Here is a comment. David Sigmund has a nice paper, and actually that's very useful for us, where he argues that, well, that's quite obvious, that of course if you have a large number of jumps, then maybe you do not want really control that you overestimate just one single jump. It's just a difficult problem, and this leads to in our situation really to a method which is quite conservative. So what you can do instead is, of course, you can look at the false discovery rate here. What does that mean? That means now the relative proportion, right, standardized with the true number of jumps, and then in a sense automatically it adapts to the size of the number of jumps. You can look at the relative proportion of falsely discovered jumps by all the detected jumps. I will not go into detail here. What we can do is actually we can modify our method. That means essentially just choose the parameter q in such a way that we can control that false detection rate. So that means we really can control the expectation of the relative number of jumps. This is, of course, a relaxation of this very strong family-wise error, but in particular in situations where you have a lot of jumps, this seems to be very useful. Here's just a picture. Here is a signal with one jump, which we estimate, and here is a signal with a lot of jumps, like that one here, right? And so if you would, for example, take a significance level of 15%, that means you want to give a guarantee to overestimate the number of jumps, which is less than 0.15. Actually, here you get a quite conservative situation, and the real probability is just 4%. With that simple jump, with that single jump, it's 0.15. So what you can do is now you can control the false discovery rate, compute the corresponding alpha to it, which is in this case actually 0.55. So you see you should relax much more. And then you got in both scenarios that you can control the false discovery rate at 0.15, and this is the corresponding estimators. So you see you get the right number of jumps. It's just that this estimate I showed you before is in that situation just too conservative. You have to relax your alpha, and a better interpretation in that situation is certainly think of in false discovery rates. There is another issue which was brought up by people. That's what happens if the variance is inhomogeneous. Here is a situation that's a variance. You see here is a jump in the variance as well, and the true signal is a black line. And so what our estimator would do here now, it would include by far too many jumps. And the reason is, of course, if the variance changes and you estimate the variance overall from the data, then in that region it starts to try to explain that large variance by segments. So we have a modification which is due to Florian Pine. He wrote his master's thesis on that topic. He is here. A very nice modification. He called it H-smooth, which just does the following, and I think also David mentioned that yesterday. You can locally now divide by the local variance, so you can come up with a new multiscale statistic, and then things become more tricky because the asymptotic theory is not so clear anymore, but you can give good bounds on that. And then in that situation, for example, you would get this red reconstruction. I will not go into detail here, just to mention that. I also mentioned briefly that at the moment we stick in the Gaussian world, but you can easily leave it. In our paper, we did it essentially for exponential families. Here's just a simple example, quantile regression. How can you do that? Well, you can rewrite quantile regression in a sense as Bernoulli regression, right? If you just take an indicator function defined when you're small and in a certain quantile. Here is a picture. That's a true median in that case, which is corrupted by Cauchy noise. So here you see all the data. So you see sometimes very, very large extremes. Here you see just the data between 0 and 10. So you can somehow recover here now a little structure of the signal, and that's what you get for a reconstruction here. So there are many ways to extend that. Okay, maybe let me wrap up in 1 minute. So what we try to do is we try to come up with an estimator which includes a model selection step, which is essentially based on a testing idea, on a multiscale testing idea, plus a minimization step which can be computed in that situation. And this gives you a constrained estimator, a constrained local maximum likelihood estimator, and I would call it maybe a multiscale regressogram. You can do it in many situations. I just showed you some applications here. It's computationally feasible. We are working on improvements, but at the moment it's between linear and quadratic time. We were very much motivated by the idea to control the probability of misspecifying the number of jumps, which gives you guides for thresholding. And it also allows you to incorporate prior information, for example, on the smallest scale. You get, well, I think hopefully quite strong statements, at least some statements for uniform confidence sets or asymptotically uniform confidence sets. There is a lot of simulation studies done by us and also done by others, which I think in essence show that the performance is quite good. The method has a tendency to, and this is how it is designed, in first order really to control the overestimation error. If you want to relax that, then it's, I think, a good idea to go to the FDR, and then you get much better probabilities to estimate the number of jumps correctly. It adapts automatically to sparseness over a very large range of scales. I did not show you these results, just mention it. And what you also can show is you can do more theory. For example, you can show that you get uniformly, in a certain sense, the optimal estimation rates, which are 1/n up to a log term. So let me just finish by saying there is software on our webpage if you are interested in the method, if you want to use it. And thanks for your patience.
Yeah. What's great stuff. Where are the limits? So I have like two kind of questions. The first one is probably easy to answer because it's probably work under progress. If you have correlation, what happens, right? The second question is more like to better understand the spirit of the conservative nature of the method and the way out. You mentioned that you can do FDR. So just a simple theoretical experiment. In your example that you showed, what would happen if you split the data into a first half and in the second half? Can you quickly adjust then the method just by taking into account that you have half the sample size, that it would still detect the small jump and still,
yeah,
because it's so,
okay.
You know, you got the question.
Yeah. Okay, I think these were actually 3 questions. So what was the first one? The first one
Correlated data.
Okay, correlated data. There is room for development, and actually I'm very happy to be here to learn more about correlated data. That's not my area. As I showed you, we did simple modifications. Simple modification mean, for example, I think I have a slide on that makes it maybe simpler. For the correlated data, you just here. So for example, what you can do is the following, but this is really just first ideas, and there is a lot of room for doing better and more sophisticated things. But imagine, for example, we have such a simple model, like a moving average process, and I showed you before an M-dependent process, essentially. So you could just do the following. You take the same statistic, and now the calibration of that statistic, or the standardization of that statistic, just comes from the variance of these observations in the independent case, which is just proportional to the square root of the length of the scale. Now here you can compute that variance as well in that specific model, right? So you would get this expression. And so what you see is actually that if you just do this little modification, then this was, I didn't show you the signal, but this was a signal with 6 jumps. Then actually you really improve the estimation of the number of jumps significantly by that knowledge. So that means this is by far not the final answer, but it's clear that if you have local correlations, and you need actually, that's what I claim, a quite good knowledge about the local correlation, how it looks like, else you cannot, in a sense, distinguish anymore between a jump and what comes from the local correlation, but let's assume you have that, then you can cook up such a method. You can come up with more sophisticated methods, maybe likelihood ratio tests in these time series models, whatever, so, but there is room for improvement, just to that. And the second question was, do you split the data?
Okay. The nature of the method.
The second question was, what happens if you split the data? That's maybe a good slide. This is data from comparative genomic hybridization profile. Where do you want to split it? No, I mean, that's an important question, because if you split it by accident close to a jump location, right, then you will never recover it anymore, okay, because if it is on a large scale, because you don't have enough data.
No, but it's more a scaling question. So split it in an innocent region, okay?
Split it in a what?
In an innocent region where there's no breakpoint.
Oh, so you know from at once there is no breakpoint.
Oh, I'm wondering if you apply your method, say, on the first half separately and on the second half separately. Can you tune your overestimation probability bound, given the data that you would basically get the same result on the separate?
Oh, you need not even to tune, it would be automatically in, because if you split your data, but I would just say it's not a sensible way to do it, but if you split your data in 2 parts, then of course you reduce essentially the set of scales, right? You do not look at the very large ones, but you get control over the maximum of all scales. So in particular, you would also get control over all these scales. So that means you would never violate the alpha, you would just be smaller. And of course you could adapt for it. So then you would simulate or compute whatever the distribution for that system of scales. So that's in. Does it answer your question?
Well, maybe we discuss it over lunch. But I understand the spirit, yeah.
Okay.
I think given the time, we maybe should put questions there, and you can always ask Axel any questions over lunch. So if we just thank Axel again.
Thank you.